Oh, what's going on? Why isn't this working? No. Okay. Here we go. So we're going to start off with definite integral. Now I know a lot of you know definite integral. The first few slides, it's more relevant to the people who are new to integration. And then after that, the questions that I've selected are hard, which I've put up on your printed out for you to actually have a go. So you can have a look at it in the meantime as I'm explaining definite integrals, but mainly properties. Mainly properties. That's what I want to talk about in the first question of 2010. And in order to understand that, you have to understand sort of the definite integral and the properties of it. Okay. Now, let's talk about for those who haven't done integration before or antiderivative. Let's just talk about what you're actually doing. So you've now learned how to integrate a few polynomial functions. I've shown you ax plus b to the power of r, where r equals -1, or r is not equal to -1. Yeah, you've learned how to integrate e to the power of kx. Okay, that's what you've been doing so far. And so the question is, once you use a fundamental theorem of calculus, you subtract, you sub in the numbers, the intervals, and you subtract each other. What does that number tell you? Okay, that's what I want to talk about today. So the example I'm going to give you is, let's say I asked you to do the definite integral of x plus 1. It's a linear, it's a straight line from -2 to 2. So if I had to draw it graphically for you, okay, this is your -2 to 2. You're integrating, and I've always told you that the integration is actually the antiderivative, and the antiderivative is the integration, and integration means the area under the curve, right? So what we can see is we've got two areas. We've got A2 and A1, right? Now, if I actually showed you the method, if you were to go through the method from the previous exercise you've done, then integration of x plus 1, you're just using the first rule. That's just the antiderivative, yeah? So add the power by 1 divided by the power by 1 times by a, right? So x becomes x squared on 2, because x to the power of 1 is 1 plus 1, which is 2. So you've got x squared on 2. And then antiderivative of x, which again, just a reminding for those who don't normally do or haven't done integration before, this is the same thing as saying 1x to the power of 0. So that's why when you do the antiderivative, it becomes x 0 plus 1 over 0 plus 1. That's why it becomes x. Okay, just in case you were wondering why it was x. So once you antiderive that, then you use a fundamental theorem of calculus, and you use a definite integral, and you sub in 2, subtract, sub in -2. So that's what I'm doing here. I'm just showing you that you are now subbing 2 in. So that's all I did. I subbed 2 into the equation, and I sub in -2 for the second one over here. Okay? And then you solve that, and what you get is fundamental theorem of calculus, you get 4. Now this would imply that you've got 4 squared units, which is the area under the curve. Okay? So between -2 to 2, if I look at this graph, from -2 to 2, it's telling me I've got 4 squared units. But here's the interesting thing is, because then if I asked you, let's find out the area of them individually, because it's a straight line, you can actually work it out through a triangle, half base times height. So if I look at this triangle, I've got currently a height of 1, because it's gone down by -1, and it's got a base length of 1 as well. So if I asked you to find the area of each one, you'd tell me half base times height, half of 1 times 1, that gives you half. Okay, so that tells me half. And then if I ask you to find the second one, same thing, it's got a distance of 3, and it's got a height of 3. So you say the area equals to 9.5. Now if you add those two together, A1 plus A2, 9.5, oh, 9 over 2, sorry, 9 over 2 plus half. Or if you can think about it, 9.5 is the same thing as 4.5. Okay, 4.5 plus 0.5 gives you a total of 5. So the question is, why is that? You see, we said over here when we integrated, you get 4 squared units. But then over here, when we actually add according to the diagram, why aren't the areas the same? You see, we add the areas, this tells me I've got 4.5 squared units. This one tells me I've got half squared units. So the question is, why is it that you add A1, A2, you get 5 squared units? And the difference is, when you find the definite integral, what it's actually doing is it's actually finding your net signed area. If you're questioning what is a net signed area is just saying overall, is my area more on the positive side, which is above the x-axis, or is it more on the negative side, which is below the x-axis? That's all you're really saying. So when you find the definite integral, it just tells you where it is. It's like if you think about distance is total area, which is on the right-hand side, or displacement. Yeah, displacement is sort of like, it's dependent on the direction or based on the origin. So whether you're moving more to the right or you're moving more to the left. So if you think about physics, the net signed area is exactly the same as displacement, and the total area, which is on this side, the total area is like distance. Okay, that's the difference between the two. And every time you find the definite integral, you're finding the net signed area, you're not actually finding the total, which is important because depending on the question they ask you, if they're asking for total distance or whatnot, you have to be able to differentiate the difference. Okay, you have to be able to tell, okay, I'm actually now finding the total area and not the net signed area. That's the only thing I wanted to make sure that you understood. Net signed area is an overall. You just want to know, am I more in the positive or more or less? Okay, because like equally, what you're saying here is this is negative half area. So it's got a half, but it's got a direction. It's below the x-axis. That's why we put a negative. We're saying it's below the x-axis by half. Here, we're saying it's 4.5, but it's positive. So that just tells me I've got 4.5 in the top region, and I've got half in the bottom. So overall, I've got 4 squared units. Okay, because you're saying you've got 4.5 positive, plus you got negative of these 0.5s. That the negative tells you a direction. That's why that gives you 4 units squared. Okay, squared units. That's the difference. All right, so if you have to understand it, the direction on where the area is, whether it's above the x-axis or below the x-axis, that's what the net sign area tells you. Okay, so on the next slide, that's what I tried to describe. I was just trying to say that for any definite integral, you're actually just finding the signed area enclosed between A to B, and I did a quick description so you understand. I was just saying that if it's above the x-axis, then it's positive, and it's below the x-axis, then it's negative. That's all I'm trying to say there. Okay, and that's why we know the area equals 4 units squared. All right. So that's the only thing you have to take out of what a definite integral is. It is to find your net signed area, and that is different from the total area. Okay, you just want to know. So it's possible to get a net signed area of 0. So it is possible that you could have a graph where you got area of 2 and area of 2. And it's okay when you integrate it, do it through the definite integral, it equals to 0. That's fine. But it does not make sense if you're talking about total area. How can that be 0? Okay, this would imply it's negative 2 and it's positive 2. So therefore your total area would equal to 2 plus 2, which is 4. Okay, so that's the difference. Now, the reason why you need to know the net signed area, because then that works in the properties. Okay, if you actually understand what definite integral is as a net sign, it works to the properties. Now on the next slide, these are the properties that you have to understand. That's in your textbook and whatnot. And the reason why I want to emphasize this, because the first question that I've got you to do over here in 2010, it was only about 29% of students in that year that could do that question. It was a very simple question. You could do it in less than 10 seconds if you understood what it was saying. And it just goes back to this properties section. You see, the properties come from the net signed area. For example, you didn't have to memorize this. You didn't have to memorize that the area between A to B, so let's say this is f of x, okay, A to B, so let's say this is A, and this is B, and you integrate, which means find the area under the curve, they're saying that this is equivalent to, if you switch the interval, instead of a to b, it is now b to a, okay, negative in front of f of x. You see, your question is like, why? Why does it just become a negative? And if you think about it logically, what this is now describing is, well, what if I had the exact same graph on the bottom from B to A? This is just exactly the same graph. I'm just doing the symmetry. I'm just doing symmetry properties here. It's just reflection. And this would have exactly the same area. It's just that it's from B to A because it's small value to the larger value. That's why if I said take that same value, if this was 10, this is also 10. Same shape, it's just reflected. You think about it like if I drew it like this, then it'd be like this. Wait, is that symmetrical? Wait, let me just do it again. There we go. Okay, so that's why if you wanted the exact same area, you can flip it, but the interval will change. See what I'm trying to say there? And so when you do other transformations as well, like when you add or subtract an extra part, you're really just moving this graph. You're just finding the area. For example, if I am taking this area, let's say same graph, okay? Same graph. If I just said, this is f of x, and I talk about a property, if I said it was from 0 to a, okay, for example, and that's my area, let's call that area 5, for example. Let's just say it's 5. If I then said, take f of x plus 3, and I want you to antidiff that, right? All I'm really saying is, that area, that's my graph, and I'm shifting it up by 3. So what does that look like? This is what it looks like. This is what it will look like. It will just shift the graph up by 3 units. So this will be added on to an extra 3. Okay? So that means this area here is still 5. The only thing is you now got an extra area of a rectangle part of an extra height of 3 because you increased it by 3. If you can see what I'm doing, I'm just taking your normal graph. If I do it like this, this might be easier to see. If I said this is from 0 to 4, and this is the area, okay? Let's call that f of x. Any diff of f of x between 0 to 4, let's say that was 5. This is my area 5. If I shift that up by 3, if I said now find the area of 0 f of x plus 3, I know you can split this interval. I know you can do this. I know you can do this. You can do 0, 4, f of x, and you use the property rule, and you split it up, and you say that's plus 0 to 4 of 3, and you integrate 3. Yes, you can. But you see, you're not really understanding what it's actually doing. If you actually understand what you're really doing, all you're really doing is this. You're just saying, if I shift the graph up by 3, so this is, I moved up by 3. So from 0, I moved up by 3. This area is still 5, but because you moved up by 3, there's that rectangle. There's this extra piece of rectangle here from 0 to 4. That area makes sense that it is 3 times the width, which is 4. And that's what you're really doing. And that's why if you sub in 0, 4, look, this is 3x, and you sub 0, 4. So any diff of 3 is 3x. You sub 4 in, it makes sense. 3 times 4, which is 12, and you sub 0 in, of course it's nothing. You see, that 12 is just telling you this area of the rectangle that you shifted the graph up. So you didn't have to antidiff it like this to actually know that it was equal to 12. I could look at that and I would have known it was 3 times the width because it shifted up the graph by 3. I knew it was a height of 3 to the width of 4. So looking at this is just transformations. Okay, if you're thinking back at this property, this is just dilations. That property there is just a dilation. It's just saying, I'll take the area, times it by a dilation factor of 2 from the x-axis. You're just stretching it. So you're multiplying the area by a certain factor. And that's what this is really saying. This is just saying times the area by a certain factor. And that's why this example, question 2010, why do so many people struggle with this? Because you all can read the transformation. If I read it quickly to you, that's just a dilation of factor 5 from the y-axis. So you're stretching along the x-axis. This is up by 3. and then dilation of factor 2 from the x-axis. So if you really have to think about it, if I had to write the transformation for this question, you're really just doing this. You're just saying 5 times x plus 3, and then you want to times it by 2y. That's the transformation. And that's what you're going to do to the area. So whatever the area is, you know you're going to times it by times it by 5 plus 3 first, and then you times it by 2. And you can actually work out the area just by looking at it. You don't actually have to do the mathematics, but I'm going to show you the mathematics, okay? Now, just in case, you're still having troubles with this section, this is just a question I took out from your textbook, question 4, to user properties. The reason why I don't like going through this is because your textbooks make it too easy. Whereas if you go through your exams and it comes up once every now and then it actually challenges your understanding about the properties. And the properties come from the definite integral. If you understand it as a net signed area, it makes sense why all this works, okay? So this whole thing that, like the first one, the reason why I don't like going through it is because it's so easy. You just look at this and say, well, 2, that's just going back to this rule. You take out 2 and you would just say, that's just take out 2 times the area. Since you know that they said integrate of h of x between 0 to 4 is 5, then you know this equals to 5, and you would just say it's 2 times 5, which is 10. See, that to me, that's never going to be in an exam. Okay, that's not an exam question. An exam question is when you play around, you do trans up by 5 and dilation by from the y-axis, which is that question that I'm showing you, okay? So I'm going to quickly jump to this question so that you can see. If you haven't had a go, I'm going to give you about a minute and a half to do this question. Question 20, 2010. It was 2010 is a nice one in terms of how hard it is. If you want a challenge, I'd say do 2010, okay? Have a look at this question. Question 20, that's the first one. See if you can apply what I've just talked about in terms of transformations, and then I'll show you how to get this answer. Okay, I'll show you mathematically and I'll show you visually as well. Okay, because if you look at it visually, it makes sense. If you do it mathematically, it also makes sense as well. Okay, so have a go with this. I know it looks intimidating, but it's just reading the transformation. It is the area, shift up by 5, dilation of factor 5 from the y-axis, and dilation of factor 2 from the x-axis. If you picture it, you can work out the area straight off the bat. Okay, it's all about picturing this graph. Shall I? "30 seconds left." All right, and time's up. All right, let's have a look. As I'm going to explain, I'm going to explain it graphically first, and then show you algebraically, because graphically is what I want you to take out of it. If you understand it graphically, it makes so much more sense that you don't have to learn these properties. You don't have to memorize it. It just makes sense what you're doing. You're reading the transformations. I'm going to draw the graph now. It says, let f be a differentiable function. Okay? Defined for all real values of x. It just means that this graph, if it's differentiable, that means you can anti-diff it. That's all it's telling you. Okay? It says your f of x is greater than or equal to 0, so it means it's above the x-axis. Then it says that x is an element from 0 to a, and this is what they tell you. They say the area under the curve between 0 to a of this function is equal to a. So if I had to visualize this, I can do anything. I can just do this. I can do that. Like I could just go, there you go. That is my f of x. I can make that up. It doesn't have to look like that. It could be anything else. But I'm going to make it look like this just so it's easy for you to visualize. Okay? So I'm going to call that f of x. So this is my f of x, and it's from 0 to a, and the area is equal to a. That's what they're saying. Now they're saying, can you please find what it would be if I did all these transformations? So if I shift the graph up by 3, stretch it horizontally, stretch it vertically, what would my new area be? That's what your job is to do, right? So what I'm seeing here is I'm seeing 2 multiplied to this entire bracket. That's what it's saying. So I'm going to read the transformation to this. I'm going to read this transformation. This says up by 3 and dilation. So this is up 3. This is dilate by factor 5 from, and this is the key part, y-axis. If it's a dilation of factor 5 from the y-axis, that means it's stretching horizontally. If it's stretching horizontally, it means it's affecting your x values. So that means in this graph here, the only thing I'm affecting right now is this coordinate, or this area, the entire area. I'm stretching it by a factor of 5. So it'll be 5 times a, it's 5a. It makes sense that it is now from 0 to 5a. So 0 times 5 is 0. So that's why my new graph is now going to be stretched. Everything's going to be stretched by a factor of 5. So the area is also now being... Wait, what's happening? My pen's not working. No! Oh, hold on a second. Oh. It's being recorded, is that why? This is so upsetting. I was just to get onto something so important, and then this has to happen. Come on, work with me.